Well, first off, thank you very much, Benjamin, and also Keith, who couldn't be here, for this opportunity. I've been aware of Google Tech Talks for a long time, and have for a long time wanted to have the privilege of being here. Thank you. This is the talk, The Case for Very Small Spacecraft. You see, we are in the mainframe era of space exploration. The systems for space exploration grew out of the Cold War 50 years plus back and were an outgrowth of the military, ICBM technology and culture, and were very large scale, very expensive. Launches tended to be very infrequent. The consequence of a failure was enormously expensive, and so on. Access to participation was extremely limited. You could get a job with one of the major companies, but that was about it. And the technical progress was actually rather slow. If you compare the evolution of rocket engine technology with, say, that of the piston engine in an equal number of decades, the piston engine technology evolved 10 times faster than rocket technology. And that's because of the culture and the cost structure in which both evolved. Oh, it's working. As I said, it was very, very expensive, and we are still living in that same environment today, except that we have lost the driving force back right after the Sputnik to the decision to go to the moon. That's done, it's over with, and now things are just coasting. And it's not going to change. It was this way with computers too. They were very big and expensive, and the only people who could get their hands on one would be large corporations or governments or universities and so on. And those who could learn to write programs and applications for them would be computer science students or employees and so on. And they were few in number, extremely expensive, and there was no large body of people working on it. Then this happened. An explosion resulted. This and its kind changed everything quickly. Suddenly, many could afford the actual experience of playing with one. I subscribed to this magazine, and oh yes. It was an explosion of a kind, a social explosion. A whole new culture grew up overnight. People were very excited about this. There were computer fairs, user groups, magazines and books, and new ways to make a living, new industries. Manufacturing of the hardware grew up very quickly. One was called Apple. A new community of people were inventing new uses and applications. There was VisiCalc, there was WordStar, there were games. One was called Doom. New class of businesses grew up. One was called Apple, and another one called Microsoft. The cost of communications collapsed to near nothing. An evolutionary pathway. The most important thing about this is that it came with an evolutionary pathway from this to that. And that's a very important feature of it. Where do I go? The world we know. Wrong button. The main thing that happened with the computers is that it was a cultural revolution. It has transformed the entire world. This very presence, all you people, are part of it and a result of it. Rather quickly, a kind of a critical mass was reached, and we're living the result. And why I'm here is to say that it's the mission of microlaunchers to do this in space. And it can be done now. The core technologies to do this are now available. It is possible, too, with a sufficiently small integrated launch system that is sufficiently small to have a kind of an evolutionary pathway that could then lead to more and more sophisticated systems, bigger, more functional, and so on, just like from that to this. And business opportunities. You could start with, eventually, when you can evolve to the point of bringing back regolith samples from the moon or from asteroids, you could just sell lunar regolith by the milligram, or put it in jewelry, what have you. Space burials, all kinds of ways to make money, plus actual exploration of space. The components for doing this are here. One of the pacing elements that triggered the microcomputer was the appearance of certain chips from Intel, the 8008 and the 8080 and so on. And that kind of was a kind of a triggering event. The parts to do this kind of thing are here now. Pager motors are now being used in model airplanes that weigh less than 1 gram. They're very cheap. CCD imagers are now very cheap and better than what NASA was using not that many years ago. And MEMS sensors, both gyroscopes and accelerometers, are quite cheap now. A 3-axis accelerometer, I think, costs $3 and something cents each. Diode lasers can be used for transmitting data. There's just a whole lot more. The raw hardware components are widely available. So what might the first kind of spacecraft be like? The sort of baseline design that I've been studying and pursuing is a spacecraft weighing perhaps 1 to 200 grams, consisting mainly of a solar cell. Where did I put my laser? Here it is. Solar cell facing the sun there, and this is the back side of it. In the shadow of the solar cell would be a can, hermetically sealed can with the electronics in it. Rather than trying to design electronics to work in a hard vacuum, just can it. That's the way the earliest satellites did, including the Sputnik. And then this would be a telescope that's steerable to aim the laser beam, which doesn't show on this picture. Oh, yes, it barely does. That shows a spot on the night side of the Earth for receiving the data. And that these things, these wings, are radiation pressure solar panels to maintain the orientation of the spacecraft. Once it's been positioned by an initial supply of, say, water in a little balloon inside here, then these panels can maintain orientation indefinitely. The panels can...
Sorry, how big would that be?
All right, for scale, this is meant to be about a 3-inch aperture telescope. The panels might be manipulated by actuators similar to those used in the 1-gram model airplane rudders. They weigh 20 milligrams, can either be homemade or purchased. You might want to Google the term 1-gram model airplane, and you'll see a community of people building these. There's one guy up in the Bay Area that I think he holds the record at 495 milligrams. That's a motor, battery, 2 channels, steerable rudder, and it flies. I'm sorry?
That's very nice.
Yes. Well, the reason that that's interesting is because if you can do that, you can do this. Also, some of the parts, piece parts and methods are directly applicable. You can buy tiny neodymium magnets now that aren't a whole lot bigger than a grain of sand or any size bigger than you want. So you can make little actuators. And in a zero-G environment, it's very simple to engineer actuators for the joints to rotate and deploy these to maintain the orientation. This is another diagram with just the parts labeled. total power budget need only be a couple watts. To maintain a 30 milliwatt laser takes about a quarter of a watt or so. And there isn't a whole lot else required in terms of power. Earlier on, I was using the figure 7 centimeters as the aperture. In reality, it may turn out to be 7.6, 3-inch, because that's a common size of silicon wafer that you can buy rather cheap. And silicon is an excellent material for making mirrors, and they're light. You can buy them in thicknesses up from a couple hundred microns up to 3 millimeters, anywhere in between. The parts are available. This is just a schematic, a notional drawing of the mechanism of the baseline type of satellite. The telescope would rotate with the mirror parked behind the solar cell, and then in deployment it would rotate out into the operating position. The angular separation between the Earth and the Sun would generally have to be more than 5 degrees or so. It would initially expand out to, say, 20 or 30 degrees, then narrow down for reasons that will become apparent a little bit later, and then could open up again. The idea is for this to go into an orbit that's slightly outside that of Earth so that you can have it appear in the night sky all the time. Easier to deal with background. Then later, through a process of evolution, you can pick a laser signal out of the daytime sky. This here beam is, if this is 3 milliwatts, that's 10 to the 16th power per second photons. And you can send a lot of information with that. More importantly, if you're doing the business, you write your own specs, and you say how much the data rate has to be, not somebody else. All it has to do is be more than 0 and be capable of evolving. This is the deployment process of that original notion of the spacecraft, where the telescope has a kind of a half tube, and the mirror can be positioned initially behind the solar cell and ahead of the electronic package. And then the deployment process, it rotates around, be driven by a little, not gear reduction, but a speed reduction motor that turns in the opposite direction, and there would be a very tiny flywheel on the motor, so the net angular momentum of this and the motor be 0. And then the only rotation of the motor of this is to maintain the Sun-Earth angle, and then the spacecraft itself would rotate around the Sun axis to keep this trained on the Earth. A CCD that's part of this will be maintaining the Earth image location, and that will be apparent shortly. The schematic of the initial notional form of telescope, this would be a silicon mirror. When I first worked out the numbers, I arbitrarily chose out of a catalog 2 millimeter thick ground so that the depth of the parabola was 1 millimeter, but you can actually cut it much finer than that. This would be about an F8. And then 7 centimeter diameter. Silicon has a very high thermal conductivity, so it'll be pretty easy to prevent thermal gradients from appearing across the mirror, which is helpful. And the idea was to have maybe a very thin metal shell around the back, everything back here painted black, and then you pump heat in or out to maintain whatever the temperature you wish it to be, perhaps at the temperature the thing was ground at. So that's why I wrote 300 K right there. Front surface of the mirror will, of course, be silvered or aluminum and have a very low emissivity. So the bulk temperature of the mirror will be almost precisely the internal radiation. There would be a 45-degree dichroic mirror, which acts as a Newtonian telescope to take the presumed infrared light from the Earth. And I was choosing 780 nanometers because that's a common wavelength for fairly high-powered laser diodes. You can now get them up to several watts. And this dichroic mirror reflects anything longer than about 700. So it would be directed to the CCD, which then images the Earth, and that's used for steering and positioning the telescope. Then mechanically aligned with a chosen quad of pixels of the CCD would be the laser position. And the task then of the system is to maintain the laser at a chosen place on the night side of the Earth. From a typical distance of 0.1 AU, typical near-Earth asteroid territory, the laser spot might be, say, 150 kilometers across. Let's see what else here. Laser itself, I was assuming 650 nanometers. That may be what this one is. Most of the cheap pointers are 650. And the original generation of discs, optical discs, are 650. Then, I'll go to the next. Here's the numbers, a little bit of number crunching from a laser downlink, assuming 30 milliwatts, 10 times this, and that's 10 to the 17 photons a second. And resolution limited 7 centimeter aperture would confine the beam to about a beam width of around 2 arc seconds. That's about 10 to the minus 10th of a steradian. And then when you work out all the numbers, you can get down to the Earth with a half-meter telescope, which is ambitious amateur-grade telescope, over 1 million photons per second. And after all the losses in the telescope and the kind of diode being used, you may be able to count 200,000 to 300,000 events per second, and then you build your data rate out of that. First, you would start with something very crude and simple, perhaps several hundred counts per bit, and then later evolve more sophisticated ways of interpreting photon to bits. And there's a lot of technology out there, and a lot of people are good at it. But the idea is to start simple with an evolutionary pathway. For the uplink, I was assuming about 1/4 of a watt coming from the Earth, same 2 arc second beam width, and then there would be, after a filter, somewhere around 10 to the 5th counts per second. Given that CCDs that are now available have a noise background or a leakage dark current of less than 1 electron per second per pixel, it's not very hard to beat the background. This is what the Earth might look like from the camera. With the, that would actually be an infrared color, not red. Oh, there it is. A typical initial class of launches is going to place the spacecraft slightly south of the plane of the Earth orbit. So the lit part of the Earth will tend to be mostly on the southern hemisphere, and then the sun angle is going to depend on how it is as the Earth is passing it. And then the task is to decide where to plant the beam for receiving. The camera, since it's the device for detecting uplink data, its entire area can receive data from anywhere on Earth. And then with an appropriate password, you can then instruct the beam to be moved over. Let's say it's cloudy in Denver, and you have to shove it over to Flagstaff. Then you send up the information, and you're good.
How big are the pixels?
Oh, they're all over the map, typically on the order of 10 microns.
No,
What matters is the number of pixels in an array.
No, I mean, how big, you're saying the pixels are going to be the beam spot. So the
Oh, yeah.
It's going to be about 150 kilometers. What do you expect the apparent spot size to be on the uplink? How big is a pixel?
Well, the pixel of a CCD might be 10 microns square. That's typical.
The ratio of pixels to square meters on the Earth's surface.
Yeah, that's not important. The CCD would be imaging the entire Earth and using a little bit of either circuitry or software to read the outer part of the Earth crescent to accurately map any location on the night side of the Earth. And then you would have mechanically assigned the intersection of 4 pixels that are somewhere near the middle of the CCD that's mechanically built in at the time you fabricate the laser and CCD holding fixture. And with fairly simple circuitry, you can identify the spot, which would be smaller than the dimension of a pixel, locate its position to within 1/10 or so of a pixel. so that the pointing accuracy of the system will be half an arc second or better. And then the gross positioning of the spacecraft would be the coarse pointing servo. And then a finer servo could be something similar to those used in those CD-ROMs. Those are precise to positional accuracy of a few tens of nanometer, and they're very simple to make. A notional initial family of launches that would be toward the east in the late afternoon using the Earth's horizon and the sun as the references for guiding the direct descent to escape. And that would put it on an orbit that is slightly exceeding the speed of the Earth at the time of launch. So its orbit will be entirely or mainly outside of the Earth orbit, going out toward Mars. If you exceed by, I think it's around 400 meters per second, the escape velocity, then you will pass the orbit of Mars. It doesn't take very much beyond escape. And the idea is, here's monthly line of sights to the spacecraft, 6 months after. And the implication here is that for the better part of the first year after launch, it's in the night sky and easy to track. An actual encounter for photographing an asteroid would probably be engineered so that the passing is done fairly soon after launch, within a month or so. I didn't get to read it, but there was an incident posted a couple days ago where an asteroid came very close, little asteroid came very close to here. And of course, we've got Apophis to talk about, the one that could conceivably, maybe, who knows, hit in 2035. Anyway, this would be a typical thing. If you go to the website that JPL runs, which is linkable off my website, more than one a day, they list the new ones as they come up. And the missed distance is listed either as kilometers, fractions of an astronomical unit, which is, in round numbers, 150 million kilometers, or multiples of the lunar distance. There are plenty of them to shoot at. So whenever the equipment is ready, there will be one to shoot at, to take pictures of. And then as the technology evolves and you have a low thrust propulsion capability built into the spacecraft, then you can attempt to rendezvous with one and then orbit it. And then be taking pictures of it for weeks or however long the electronics will last while it's orbiting, and maybe invent little tiny spider-like things that could be kicked free of the spacecraft by a spring with enough velocity to counter the orbit velocity, so it'll drop straight down and you have something. Quite a few years ago, back in '93, when I was president of a amateur rocket club called the Pacific Rocket Society, some people in NSS, National Space Society, put up some money to fund the development of what was to have been the first amateur rocket to reach space. And at that time, they set the limit at 50 miles. Later, our calculations showed that this would exceed 100 kilometers. And this was a rocket using LOX and 75% ethanol, V2 fuel. And it was to be 2/3 by mass propellant. In other words, the takeoff weight was 67% propellant. And the tanks were a set of 6 irrigation tubing tanks, tubes, 4-inch diameter by 15 feet long, and they held altogether 200 liters of propellant. And the hardware worked. This is the rather ugly engine. This is regular 4-inch Schedule 10 steel pipe. And inside of that, by fortuitous accident of pipe sizes and whatnot, copper pipe fits inside that with just enough radial clearance inside to make a fairly good set of passages for the regen cooling using the fuel as the coolant. This engine looks a bit funny because there are 3 inlets. The original design was to have a valve on the bottom of each of the tanks and an independent connection to the engine, and each valve would have been regulated to see that all of the propellants drained equally from the tanks so that no tank ran dry before others. That helps with the rocket performance because the engine will tend to quit if either of the propellants runs out first, and then whatever's left, they call it residual, and it's dead weight. This worked. Unfortunately, the organization didn't, but that's another story. CanSat launcher. With the help of some friends running some calculations, we went through some sample designs of 2 or 3 forms of micro-launcher vehicle. And one was to be directed at the population of people who were making CanSats. That's this exact size and shape and a maximum weight of 350 grams, which happens to be the weight of a full can of beer. So I think that's where the inspiration came from. One of the criteria was to see that the vehicles, at least first stage, would stay under a certain total size. That's this size, Newton seconds of total impulse. This is how the FAA classifies rocket size. If it's under that, it would be called, now with the new regulations, a Class 3 high-power amateur rocket. And if it can be kept under that size, the regulatory situation is much, much, much simpler. So that's where to start. And then when you're able to operate this as an amateur rocket and stay within the limits imposed, you can build launch experience, get the hardware working well. Each launch may only cost about $100, mainly the expendables. And if you recover the rocket, it is. If the rocket has to get bent, then of course it'll be a little more. And then later scale up the size of the rocket. A CubeSat rocket would be somewhat larger. Our calculations showed between 1 and 200 kilograms to place a 1 kilogram CubeSat to LEO, or about 100 grams to escape. And that was to be defined as the entry-level ML1, entry-level micro-launcher vehicle. Then something new came along, and I'll get to that shortly, the Enterprise. Calculations, spreadsheet calculations for planning the ascent of the first stage were done. And what this plot shows is 2 different circumstances. One where the engine was simply run at full throttle all the way. And this curve here is the Q, or dynamic pressure, one of the main stresses on a first stage of a rocket as it's climbing. And then the other was where I would use a pitot tube to servo the engine to flatten the Q to some arbitrarily chosen maximum value. The one for this calculation is 33 kilopascals, which is equal to about 450 knots, equivalent airspeed at sea level. In the aircraft business, they call that KIAS. It's knots indicated airspeed. It's what a pitot tube would read on an airplane, regardless of your altitude. And then this peaky curve here is the velocity, and then this curve here is the ascent to peak ascent. He didn't bother plotting the return. In both cases, the peak altitude exceeded 100 kilometers. That's 100 right there. And it showed that, in both cases, this rocket was 60% propellant at liftoff, or a mass ratio of 2.5. And it's eminently practical. In scaling down the size of a rocket, various ratios of physical processes change. And one of the things that impairs somewhat the performance of very small rockets is air drag, being a larger fraction of the total energy required. But it turns out to be quite doable and quite manageable. The upper stages would be working in a hard vacuum, and rockets of even 10 Newton thrust, 1 kilogram thrust, work nearly almost as well as larger engines. This might be a typical trajectory for the first stage and staging, where the first stage would accelerate as quickly as possible at maximum engine thrust. And then at some point, when the pitot tube showed Q rising to the point where it had to be limited, the engine would be throttled down to maintain the Q to be constant. Then at some point, the engine would gradually be throttling up as more and more of the load was due to acceleration. Then at some point, the engine would return to 100% thrust, continue rising to thinner air, and then the Q would diminish. And then at around 30 kilometers altitude, the main propellant would be depleted, and this would reach a velocity of around 1,200 meters per second. And then in this particular design, it would be desirable to maintain the engine running at a very low level, just enough to overcome the drag, residual drag, plus maybe a 1/10 or 1/20th of a gravity, so the propellants in all the stages remain settled on the bottoms of the tanks. Staging would take place perhaps at 60 kilometers, and it's substantially a vacuum as far as engine performance goes. And then the two additional stages, the second stage being designed to produce a fairly high acceleration, let's say beginning at twice gravity, and produce a total velocity increase of 2 or 3 kilometers per second. And then the balance done by a lighter constructed third stage at lower acceleration. By aiming to the east, you can take advantage of a free ride, courtesy of Earth's rotation. And the initial notion was to have an eastward, a horizontal component to the trajectory being around 600 meters per second at the peak. Added to that would give 1 kilometer per second of eastward velocity at the time of staging. So to go to escape, the pair had to exceed 10 kilometers per second, not 11. And a recovery plan was being considered, which involves having cruise missile-like wings sprout and have it glide and then be picked up, taken in tow. This method might make sense for somewhat larger stages than are contemplated here. A simpler method might be to use a parachute. In either case, air brake-like panels would be deployed while in very thin air up here, and they would produce enough drag so that when it got down to a fairly low altitude, the indicated airspeed would be under 200 knots, which is good enough for parachutes or the deployment of wings.
Why bother to recover the booster? Why not?
It's economics. Some people are into recoverable rockets and some are not. In the case of, I'll get to that shortly, the Enterprise vehicle, it may turn out to be better to let it go because the hardware cost of each first stage, I'm estimating at about $200. And if it has to fly out to sea, it's more expensive and risky to go out and fish it than let it go. But at an expensive first stage, then the economics might go for doing something like this. There is a lot of interest in making stages recoverable. Strategy for bringing this about involves a whole lot of things other than just the rocket science. One way to think of working environments is a kind of entropy. Some environments, like here or in a shop or your office where you're diddling with one of these, is cheap. And there's no regulations, practically none. And then the most exotic and expensive of the environments would be when you're doing launches somewhere, because you have to have a license. And oddly enough, in this country, you need an export license because you're exporting hardware to space. Go figure, but there it is. Anyway, the microlauncher work could be reduced to 4 locations, and I'll enumerate them later. And then also the design of the equipment and the procedures could be designed to fit the regulatory situation as it is now. And then another key thing to work for is a low entry threshold. Because the barrier is getting started. Once the barrier is over, there's going to be it's going to be a whole lot easier for more people to get into it, making a community. A good example might be what the Wright brothers did. People were for some time trying to make an airplane heavier than air work. Finally, they did. They invented something more important than the airplane. They invented the fact of the airplane, and that's what got aviation started, not the airplane itself. So what we need is a fact of little launchers. Doesn't matter how small they are. They have to be a fact. 4 locations could be the shop where all the design and fabricating and ground tests can be done. No FAA involvement whatsoever. Nothing flies. Then the next location might be a nearby adjacent place for low altitude tests in uncontrolled airspace, called G airspace in aviation parlance. The requirements for flying rockets in uncontrolled airspace amount to a 24 to 72-hour notice to the nearest air traffic control. And that's it. There's no permit, nothing. And then a location 3, when it's necessary to fly to higher altitudes, staying within the amateur rocket regulations, you can go as high as 150 kilometers now. And there are some places within the United States where you can do flights this high. The amateur rocket rules require that you have clear radius around you equal to 1/4 of the peak altitude. And so there are some places in the US where you can get a 25-kilometer radius around your launch site. The Black Rock Desert in northern Nevada is one of them. Then the most exotic of the locations would be the space launch. Presumably, it would be done on the East Coast because the FAA would probably require it, but that's not a given. Could be that they might allow inland launch in the western US or West Texas would be attractive. For a vehicle this small, they may allow it, but it might be safe just to assume that you have to launch out over the Atlantic from the East Coast. The regulatory environment. The simplest, well, I should have maybe had a separate item up here. None. If it doesn't fly, the FAA doesn't care. The simplest set of regulations has to do with amateur rockets, which has been defined in fair detail rather rigorously, and it's now in the Code of Federal Regulations, and it's also available off the FAA website. That defines the now requirements for hobby-type rockets, and they're using the word amateur, not necessarily characterize the kind of people doing it, but it is a technical term that refers to non-professional or non-military or non-commercial vehicles. And no longer is the time of burning of the engine restricted. It used to be restricted to 15 seconds. Now it is not at all. And they have set a new altitude peak where the rocket cannot reach 150 kilometers altitude. That's 92 miles. And there isn't a whole lot else involved in this. If it rises into controlled airspace, there is a procedure where you have to file a notification 45 days in advance. Then the next thing is the launch license by the FAA, which is a close to 6-month-long procedure, somewhat tedious and manpower intensive, but it's done. And the procedures are precisely defined and already published and so on. And then the oddball is export license. Why they care about exporting something to an asteroid, I do not know. Yes?
In order to get the launch license, you have to provide basically insurance.
That's a requirement of a launch license, and it depends on the circumstance, and the FAA tells you how much you have to get. A vehicle this small, it'll probably be close to the minimum that's available.
It's still pretty big, right?
It's a significant budget item. It's an annual expense. It's like car insurance. And I know people who are buying it, and it just has to be on the budget. It's probably the most expensive single item in a development project. But hopefully the small size will permit it to be at the bottom of availability.
So in order to change those insurance rules, we would have to actually change the set of
The weakness of the whole insurance thing is that the government tends to mandate insurance without mandating that it be available, and that's been a hang-up.
Well, that's true, but it's liable for damages that happen to other countries. So
Yeah, but are you going to kill somebody with a rocket that weighs less than a pound?
if it's designed for successful reentry. If it's designed for successful reentry.
Oh, re-entry is another whole kettle of fish. There's a separate license for that, so they're ahead of you. No, in 1986, they published in the CFR all the regulations required to quarantine material brought in from other planets. That's done. They're ahead of us. Regulations.
Is there going to be an effort to alter those rules internationally so that the insurance and other things can better benefit these micro-launchers?
Well, no, what really has to happen is that there has to be a market for insurance, then companies will provide it. This is so rare and done so infrequently that there's no established market for insurance, and I think that's the main problem. I think. Early entry threshold, the going from PowerPoints to hardware is a barrier. Few people have crossed it. And that is the main problem, and that's why people aren't doing it yet. A low entry-level threshold that my friends and I have been looking at was the CubeSat launch service. There's roughly 100 or so in the United States alone. CubeSat's waiting for a ride somehow. University built ones. The students who collaborated in building them will have generally graduated long before the thing flies. I tend to term these tabletop spacecraft. They look great on a coffee table, and that's often as far as they get. Something new came up called the Enterprise. A Dr. Paul Deere from England proposed a kind of a whimsical thing at a website called brain freeze. It'll come back to me. It'll come back to me, the website. It's a site where people propose strange ideas, and then the people on the site vote for this or that idea being clever. They like the Enterprise idea so much that he decided to actually announce it as a formal prize, and he himself is putting up the money, 10,000 pounds. What happened? Oh, I see. I accidentally bumped the thing. The previous, let me see if I can go back. Yep. Going back. And prize. Space burials is an interesting possible way to make some cash revenue. Back in '82, there was a space company called Space Services Incorporated, set up by a wealthy real estate guy in Houston area and some others. And it didn't work out very well, but in the meantime, some funeral people got together and organized a company designed to place into orbit 1 or so gram samples of cremated remains for a fee. And a company is now operating called either Celestis Incorporated or Space Services Incorporated. They're using both names interchangeably, I think. In their entire history of 17 or so years, they have placed, I think it's 85 sets of remains in 3 of 4 successful satellite launches, always as secondary payloads contracted with a launcher, which I believe has been in each case Orbital Science, but I'm not sure. Anyway, 85 divided by 17 years, it's not a volume business. And it will never be unless the venture owns its own launch means. And then a Microlaunchers vehicle could place perhaps 100 sets, samples that weigh a gram or so each to escape, and perhaps reasonably charge a fee of perhaps 10,000 per. And so there's a gross of approaching $1 million per flight. And we seem not to be running out of dead people, so this may work. It's been studied economically, and it looks like a serious business model. It could work.
Just back in a moment, almost all of those CubeSat projects
Yes.
have an included budget of between 50 and 100,000 for launch services. So it's not like the money's not there, it's just a bit space available and structure on existing launch platforms.
The problem with secondary payloads is you have to find somebody with a big expensive rocket and a big expensive payload willing to take them on.
That does in fact pose a real market
Oh.
for microlaunchers.
Very small market, and I've already been talking to some of the CubeSat owners.
Okay, it just sounded like
Yeah.
you dismissed it. And I was like,
Basically, they're saying, okay, get the system working and then we'll come and buy rides. Well, that's nice, but it'll be a very small market, and again, it's the low Earth orbit, and it won't be in very high volume. And due to a recent event not so long ago, there's going to be increased resistance to populating low Earth orbit with frivolous payloads. Yes.
at least without guarantees of return in the 25-year time period.
Oh, yeah, well, a CubeSat ordinarily would be coming down in a month or two because they're not put very high up and they're very low mass, frontal area, drag, all that. An Enterprise satellite, by the way, it'd be lucky if it stays up 2 days. Anyway, CubeSat launch service. Enterprise is this interesting low-level thing where the satellite has to weigh less than 20 grams. And a preliminary vehicle design is that it could weigh 60 kilograms or less total off-the-ground weight. In the rocket parlance, GLOW, gross liftoff weight. And that's model rocket size. The model rocket people have been flying rockets much bigger than that. Space burials. First stage marketed as a sounding rocket. People that want to fly experiments to 100 kilometers. There's a very tiny market. Some people are pursuing it. And the first stage developed as a launcher could simply use the lifting capacity of the upper stages as payload and fly it as a sounding rocket. This would make especially good sense if this were recoverable. Then it's just wear and tear per flight. And the per flight cost to lift, say, 10 or 15 kilograms to 100 kilometers might only be a couple $100. That's the cost. It's not what one would charge, of course. What did I do? I think I have to put this in the right direction again. Vehicle growth, okay. Enterprise vehicle, 60 kilogram GLOW, and it's only an estimate right now, based on the performance of the third stage engine. There is such a large multiplying effect with rockets, where the lower stages have to carry the upper stages, that any slight improvement in the performance of the third stage engine permits greatly reducing the size of the base vehicle. I made an estimate of a particular level of performance in a vacuum of 250 seconds specific impulse, and the engine weighing 50 grams, and that resulted in this estimate. Should the engine specific impulse be slightly better than 250, then this can be actually quite a lot smaller, perhaps even half of that. The next level, the so-called CubeSat launcher, or the ML entry level, was to weigh between 1 and 200 kilograms off the ground and be able to take either 1 kilogram to LEO or 1 to 200 grams to escape there. And if you scale up the size of the vehicle, the fraction of its gross liftoff weight that could be payload can actually increase greater than the ratio of the vehicle itself. If it were scaled up by a factor of 10, 1 to 2 ton liftoff weight, 2 to 3 kilograms could be taken to escape, which would permit landing 1 full kilogram onto lunar surface. As a rule of thumb, 2/3 of the mass would be the landing means. And GLXP is something worth talking about. Some of you may have heard of that. There are, I believe now, 18 entrants to this. The top prize is $20 million. And I think only 1 or 2 of the entrants are thinking in terms of a vertically integrated system with their own launch means. Who knows? But being able to land little things on the moon, there's a way to do business with that. Some years ago, I think it was around the year 2000, there was a company formed called Lunacorp, and they had some kind of a deal with Radio Shack as a sponsor. And they were going to rent time on a rover running around on the moon or something. If a landing system could be as light as a kilogram each, there's nothing to stop you from putting hundreds of landers in different spots on the moon. We've only looked at 18, I forget the total number of sites being landed upon. There's things to be learned, even if you have 200 or 300 or 1,000 sites landed upon. Who knows? Okay, let's see, this is getting into the business of how to proceed, and one of the elements of a strategy required is to recruit various forms of help. This 1 in 10,000 is just a notional figure, meaning to find among the wide population of people with wide interests and beliefs and all that, a few people who like the idea to the point of being ready to commit to making it happen. And I just call them 1 in 10,000. I have no idea what this ratio will be. Seek sponsors and angel investors. Several slides back when I was showing that spacecraft image, the electronic package of that spacecraft could be a beverage can. They weigh 13 grams and they're fairly well built. And if they happen to have the label still on the sides, there's a sponsorship possibility. Oh, I did it again. Okay, SBIRs, they're rather difficult and tedious and very difficult to prepare, but quite a few companies are doing them, and various components of the system could be subjects of an SBIR. In particular, perhaps the laser comlink, and also testing the third stage of an Enterprise vehicle would entail building a basically tabletop test stand that's small enough so you could be sitting right in front of it, just put on a pair of goggles and push the button and measure its performance, and then offer that as a kit for educational purposes or what have you. That could be the subject of SBIRs. Also, spin-off companies to market components. Again, the laser data link, the engine testing kits, and so on. And a spin-off company not only provides income, but it provides an opportunity for seeking investors. Some of the components that might be developed as parts of the microlauncher system or technically adjacent. The towback recovery method itself might be marketable. There's always been interest in recovering drones and the like. CAMSAT and CubeSat launcher for fee. The winged recovery of the stage 1 could be a recoverable sounding rocket, which could be used over and over again and earn money with that. Turbopump engine, which I've not discussed as part of the microlauncher effort, because as rocket science goes, a turbopump engine for the first stage doesn't make a whole lot of sense unless you're trying to make it quite a bit bigger than initially thought about. But I've been working on a turbopump engine design.
So your booster would be like helium pressurized or something?
Not helium, no. That's too expensive these days. There's other ways to do it. The 93 design was going to use liquid nitrogen and a little heat exchanger, and it turns out the Russians had been doing it for 50 years. At the time, I wasn't aware of it. The Soyuz is pressurized with a liquid nitrogen pressurizer. Laser data link, optical guidance method. The guidance for both escape velocity and Enterprise entrance will be entirely optically based, and I don't know to what level of detail I'm going to be publishing that. Haven't decided. But anyway, components could be themselves products. So the idea is that we can try to create a community of people, a population of people with interests who would coalesce, get excited about it, work, make things happen, just like with the computer. And Then they would develop and improve in their skills at making, designing, and operating spacecraft and flights or missions. I prefer the word flight. Mission sounds too military. Yeah. And we can open access to the inner solar system and then to the lunar surface. Nice thing about the inner solar system is that the spacecraft are not going to be running into each other. There's literally trillions of times as much volume of space out there than LEO. And based on everything I've studied, I don't think any other means of opening a space age as such is going to work. The present large-scale systems are going to perform as they are now, meaning basically just churn along in a kind of a stasis where one program feeds on another, and they're just eating each other all the time. So the idea is bring back the 70s, and the hardware to do this is available now, off the shelf, not expensive. And the key is to design this so that there can be an evolutionary pathway so that it barely works. This had 4 kilobytes, I think, of RAM. Couldn't do much, except become that. And then stimulate interest and involvement. People are bored about just reading about space and paying taxes for it. Participate directly, as with this. And then create a startup venture environment, just like this was a fountain of companies being started, this being one. It can happen. So the idea is to move past the mainframe era of space. And are there questions? Yes?
So, thinking another spin-off business from this would in fact be the need for extended launch guidance. That you need to have outside of direct line of sight, the launch site, you still need to maintain guidance. You're talking about optical guidance. You'll need a mesh of already in orbit satellites. Why not make
Well, okay, here's the answer to that. One, if you're generating the requirements, you're free to generate the requirements, period. Who says that it has to be out of line of sight? Why not simply build a system that is line of sight and deal with that for now?
How do you maintain line of sight through an orbital path?
You don't orbit things. You send them out to between Earth and Mars, and they're in sight every night,
I see.
all night long.
Okay, but I mean, that specific idea of escape velocity payloads
Yeah.
is for one specific business opportunity.
No, it's for a class of business opportunities. Anything to do with the moon, loose, high-altitude lunar orbits that are highly elliptical are energy-wise very easy to achieve. That is, you barely exceed escape, and you can get put something into a lunar orbit which zips down to close to the moon and then loops out far for initially, and then later when propulsion improves, low lunar orbit and then landings, orbiting NEOs and so on. I mean, there's a lot of things to do.
So when the Earth turns, we just sort of wait until it turns back?
Why not? If you're looking at Mars, don't you wait until it's up there again?
Well, I'm thinking
When
that
it sets, you wait.
You can offer the business of not having to force people to wait.
Yeah, but why not first just make the business work at all, cross the threshold, and then build things? In other words, evolve.
That's exactly what I'm thinking.
Yeah.
Walk before you run.
Yeah. So, excuse me, the place to walk is line of sight restrictions imposed by this method, and then evolve from there. A way to get around the line of sight problem is, of course, to design and deploy someday some kind of a space floating relay that might be in a halo orbit beyond the Earth sun system, and be able to relay anytime something from far elsewhere in the solar system. But all that is far away. There's no point in even thinking about it, except to create now, in the near term, an evolutionary pathway that could lead there.
You don't think a CANSAT that can do relay and mesh looks more like that Altair than a supercomputer?
Well, okay, this whole LEO satellite business, all they are collisions waiting to happen. And besides, okay, here's one. Remember Heinlein's famous remark, you get to low Earth orbit and you're halfway to anywhere in the solar system? Well, get to low Earth orbit and you're only halfway to anywhere in the solar system. Space exploration no longer, there's nothing to discover within the gravity field of the Earth. Yeah, but support services meaning what are you trying to integrate yourself with?
Two things. First of all, the direct, so that you no longer have to worry about line of sight to your payload, wherever, no matter where you are,
Yeah.
where it is. Second, you actually now have a mesh of low Earth orbiting satellites, 2 or 3 that can individually sustain 2 or 3 dropping out.
Or collide with things.
Absolutely. If they get wiped out by, flecks of paint or whatever, then 2 or 3 got wiped out. 5 or 6 got wiped out.
Or they collide with each other and generate a field of debris that threatens everything. In any case, low Earth orbit is okay, but fixating on that is, to me, pointless because there's really nothing much to discover in low Earth orbit. And all you do is, well, there's just limited things you can do. Space begins beyond escape velocity or onto the moon, which is basically beyond escape velocity. So why not just start there?
I don't think that the only distinction about low Earth orbit is that they're completely ignoring it or fixating on it. I think they're using it and building on it. And that's all I was proposing.
Yeah, it's all right. Maybe one way is finding a paying customer who would pay for this or that service involving low Earth orbit. Absent a paying customer, it doesn't seem to make much sense. At least that's the notion that I base this on. And low Earth orbit, again, the satellites are hidden from view 99% of the time. And then when they are above the horizon, they're zipping right across the sky in a way that's hard to track. Whereas something in between Earth and Mars is moving so slowly across the sky that any astronomer can reacquire and point his telescope at it. A telescope with this big an aperture can take the data down. You can have data parties, just like they have star parties. And you could maybe even have contests where they would have coded data sent at various rates, and whoever gets it all gets a prize or something, I don't know. Yeah?
What kind of flights have you been able to make so far?
The only hardware project that I got into was that old 93 design, but unfortunately the organization came undone. The design is going to be based on extrapolations of that technology and forward. And that's basically it. Even though I'm located in Mojave, California, the opportunities to fly things there aren't very great.
So have all your hardware work been sort of just like hockey cable on the ground, little amateur rocket types?
I've not been bothering to fly amateur rockets as such because they don't contribute to the level of technology needed for this kind of thing. I'm sorry.
What kind of plans are you making for the future to try to achieve vision?
To reach the threshold where the shop can be built somewhere in the United States. And one of the possible locations might be southern Nevada. And then developing on the ground some of the critical hardware components and then beginning to fly them. In the previous slide, if I can't locate it quickly, the one where I showed the set of environments for working. The idea is to design the work, the project, so that you start in the simplest environment first. And a certain amount of commercial products could be developed without flying something and encountering the regulation problem. Then the next step would be the amateur rocket rules, which are pretty simple to cope with. So, any other questions? Yes.
Is there a business in providing a dustpan and brush service? I mean, how good is your delta V and the ability to be a non-fragmenting, damage-absorbing payload?
I'm sorry, I missed the
The low Earth orbit
yeah.
piles of sub-inch space junk is a real issue, but you've got a reasonable amount of delta V and a payload which is enough to go off and pick stuff up if you can chase it down?
Oh, okay, there have been a lot of proposals for trying to rendezvous with space junk and bring it down into orbit. I would think, and a lot of people also think, that the expense and difficulty of doing that is so great, and there is so much quantity of little bitty parts. There's no way you could make a business plan of trying to pick them up.
No, perhaps I should put it differently. In terms of cost per a delta V for recovery of,
Mhm.
you've got a few hundred items that you've realized you do care about. Are you efficient in terms of delta V to go chasing stuff down?
It's very difficult. The only efficient way to use a rocket is to build all the velocity as close to the ground as possible, just clear of the atmosphere, so you have a vacuum, and then coast the rest of the way. Doing any of these kind of maneuvers where you have to take quantities of propellant gets to be very expensive. For example, geostationary orbits require almost as much propellant as landing on the moon, and definitely more than a lunar orbit.
Getting back from geostationary takes a third as much as just getting into orbit.
No, yeah, because you could deorbit something and drop in, yeah,
You need to put 2.7 kilometers per second into orbit.
and reach the Earth. But again, what does that lead to?
Maybe a grant.
Okay, a grant. Why not?
But as he said, maybe there's 200 objects. that
I've heard several proposals, the LEO proposals that might be worth thinking about. One was to be able to develop a reusable, say, 5-kilogram reentry vehicle that you could place into orbit, run experiments for people for a fee, then have it come back several weeks later, I suppose. But you'd have to charge a lot for it, and you have another special license for a reentry vehicle to deal with.
About your 200-gram Explorer satellite.
Yeah.
So
You mean spacecraft, not satellite?
Sure.
Yeah.
Spacecraft. So F8 telescope with a 3-inch aperture. You're talking about a 24-inch light path to the sensor. Seems like at that point the fairing size of something that can encapsulate that and carry it out.
The fairing is, good question. The fairing is part of the first stage, so it can be fairly heavy, and it only goes up 60 kilometers. The notion there was the spacecraft would fold itself up in some way, and I don't know what the F number of the telescope has to be, whether it might be worth grinding mirrors that are F4 or something, I don't know.
Well, at that point, then you get back to your silicon disk becomes thicker and harder.
But you can, I've seen listings of off-the-shelf product that's up to 3 millimeter thick. So.
You can shake the backside in order to relieve the additional mass from that.
Oh, the mass isn't the question. The estimated mass for the 2 millimeter thick one was 15 grams. In other words, that's not the real issue.
Well, then if you wanted to go to a very short telescope with like F2, F1,
Yeah.
something like that, you would have a rather extreme curvature. But you can polish both sides of the mirror
I agree.
to reduce the mass
Yeah.
of the silicon.
But I'm not sure it's really that necessary to have F2 or F3. What's wrong with F8?
But
How big is the frame to deploy that length? How easy is that to stabilize? Not to dismiss, just to
Yeah.
accept that there may be benefits.
you're not going to just polish the other side anyway. You're just going to etch the thing down into a honeycomb anyway.
Correct.
What-
Remove the material.
Except the easiest way is to have a flat silicon disc that you polish a regular parabola shape.
That's the simplest fabrication.
And why not start with what's simple and then evolve from there?
Sure.
And the amount of expertise in making small telescopes is vast.
Well, but not with the whole structure being that lightweight. I mean, you're going to have
That's-
serious vibration.
yes, but what vibration? That's the deal is it should be none. Nothing's moving, nothing's crawling, nothing.
Every time you have to aim to a different point on the Earth, even though
If the telescope is designed right, I was thinking in terms of a drive mechanics that has a certain amount of gear reduction, but probably not using actual gears, let's say 1,000 to 1. And then have the moment of it, and have it so that the motor rotates in the opposite direction to the telescope's rotation, and have a small flywheel with enough inertia.
well, that would keep the whole structure from rotating.
Yes.
But it would not, but as the structure changes shape and then stops changing shape, you would
Why would the structure change shape?
because you repointed the telescope. So you started it moving
Yeah, but if the mechanics are designed right, on the first order, there'll be no angular change in the spacecraft position at all.
That's not one of
You can cancel it.
That's right, absolutely, that's done.
Yeah.
But the question still, as the spacecraft reconfigures itself during the repointing, it will have two moments added to the mass, and both of those have to be are you able to wait?
All right, this is a level of detail that's not necessary to get involved in right now, but the minor pointing of shifting the aiming spot on the night side of the Earth from, say, Arizona to Texas is such a small change that a second level servo that I was assuming was going to be part of the mechanism, not shown here, was that for a given spacecraft position, the CCD or one of the optical elements can cause the image to divert by maybe an arc minute. And that would take out any disturbances in the spacecraft or whatever, especially if it happened to have onboard propulsion, which so far,
And then eventually the little arms would restabilize any vibration.
yes. The radiation pressure is ample in terms of the amount of force it produces for this. In fact, it wasn't the first of the Mariners, didn't they use radiation panels on the outboard ends of the solar panels? There were angled little paddles, I believe that's what they were for.
Not familiar with that.
1964, okay. I think it was, yeah.
All right, we're over.
Okay, thank you so much. I enjoyed this. Thank you.